right, people. Hope we're doing well. This is a couple examples of definite integrals. So let's go ahead and get started. This one right here is a little bit of a problem for us because if I actually take out a secant tangent, all I have left over is a tangent. And I know that that's actually not going to be the case because tangent, as your u, needs a secant squared. The only thing left to do, which may seem problematic at the beginning, is to turn tangent squared into secant squared x minus 1 times secant x dx. That, when you distribute, winds up giving me secant cubed x minus secant x dx. Well, here's the thing. We already dealt with secant cubed x as an integral in a past video, so I'm not going to rework that right now. I'm going to use the insight from it, and its integral was 1/2 secant x tangent x. And for those of you who are like, I don't remember that, what we did was we actually pulled secant cubed apart into secant and secant squared and used parts. So go back and review that if at your leisure. And so we have natural log of secant x plus tangent x. And that right there, okay, this right here was the integral of secant cubed x dx. We also, in a previous video, showed the fact that the derivative of secant is natural log secant x plus tangent x, right? And that all of which needs to be done from 0 to 4. So that right there winds up being the secant x dx. So that's both parts of that integral right up there. Well, obviously there is some simplification that can be done because the second and the third term are indeed like terms. So let's go ahead, and 1/2 minus 2/2 is going to be negative 1/2 natural log of secant x plus tangent x, and we're going to evaluate that from 0 to pi over 4. Now when we do that, we just have to be careful, that's all. So 1/2 secant of pi over 4 tangent of pi over 4 minus 1/2 natural log secant of pi over 4 plus tangent of pi over 4, and that is, of course, big F of pi over 4. Then I need to do the big F of 0, and that's 1/2 secant of 0 tangent of 0 minus 1/2 natural log secant of 0 plus tangent of 0. So let's start, that's supposed to be a 0, not a theta. Let's start basically figuring out what these values are. Now, secant of pi over 4 is the reciprocal of cosine of pi over 4. And remember that cosine of pi over 4, if you remember all the way back to unit circle, actually came from the ratio of 1 over root 2. We then rationalized the denominator and turned it into root 2 over 2, but really it's the reciprocal of root 2. And so secant pi over 4 is just root 2. Tangent of pi over 4 you should know is 1. This is root 2. This is 1. Secant of 0 is 1. Tangent of 0 is 0. Secant of 0 is 1. Tangent of 0 is 0. Well, this right here is 1/2 times 1 times 0. Okay, that's 0. This becomes 1/2 natural log of 1, because secant 0 actually does give you a value, but if you remember, natural log of 1 is also 0. So this whole second thing right here, both of those terms amount to 0, so the full value actually comes out of here. And what I get is I get 1/2 root 2 minus 1/2 natural log root 2 plus 1, and that is approximately 0.266. And you can confirm that with your calculator, but you need to remember that, and let's go ahead and just for giggles, let's go ahead and do this integral on our calculator just so we remember how. Remember that the integral stuff is right here under Windows. You have to use alpha and F2. There's a little F2 right there. So you press alpha, window, and you get that pop-up menu. And of course you can do number 4, which is integrals. We go from 0 to pi over 4, right? And you just got to be careful with the parentheses on these. That's tangent x squared. And then, of course, times secant. But we don't have a secant button. We have to do, basically have to do over 1 over cosine. And you can basically put it as its own fraction, or you can put it, put cosine in the denominator. And so actually that really winds up being sine squared over cosine cubed, but, details. And there you go, 0.266. Now, alternatively, remember that you can go to y1 and take this, take the integrand and actually plop it in there as the function, as y1. And then when you're back here on the main screen and you want to do your integral, you can go from 0 to pi over 4, and all you have to do is plop in the y1. Now, you might think that's more work. Yeah, but it also allows you to see the graph, which is kind of the whole reason you put it into the y1. And we, basically press enter and we get 0.266 again. So our calculator confirms that we haven't made any mistakes on that one. Either that or we and the guys at Texas Instruments both made a mistake. But at least we're in good company, right? All right, now this one looks a little bit daunting. And you look at it and you're like, it's got a radical in it, I don't know. But here's the thing. Doesn't this bear a striking resemblance to that? Well, I also happen to know that that is the power reducing formula. That's the power reducing formula. Now, you could alternatively put cosine of 2x, and that can be 2 cosine squared x minus 1, and you could substitute that in. But either way, what you're really going to get is you're eventually going to get root 2, which you can pull out, and then the square root of cosine squared x dx, whether you use it by power reducing, because you see the similarity there, or whether you just plug in this and simplify. Now, you get the square root of cosine squared. Now remember, anytime you're taking the square root of a square, you need to be very careful that you put it in absolute value bars when you actually simplify it. And that's because the radical, by necessity, is going to spit out positive values, and basically the absolute value bars sort of unnegativize any potential negatives. But we know that cosine is not always negative. And actually, we know the values that we're using for cosine. We're using values between 0 and pi over 6. And between 0 and pi over 6, well, cosine's positive, so it doesn't need the absolute value bars. I just get regular old cosine. Now, that means that it just integrates into regular old sine, and I need to evaluate it from 0 to pi over 6. That means I'm going to have root 2 of sine pi over 6 minus sine of 0. Sine of 0 is, of course, just 0. Sine of pi over 6 is 1/2, and I get root 2 over 2, which is approximately 0.707. Okay. I would actually rather have the exact answer, but if you need to put the approximation for some reason, then by all means do it. Okay. Now, let's go ahead and move on to yet another one, and here we go. Now, that right there is one that we've actually seen before, or we've seen one, like it. And we see the fact that they are both of the same degree, but they're also both odd. And here's the thing. which one should I choose to leave as the residual du? And the answer is it doesn't matter, actually. What matters is just choosing one way to do it and then just doing it. So let's do it both ways. Let's do sine cubed of x and 1 minus sine squared of x, leaving behind that remaining cosine to pair up with my dx in order to make my du. What happens here then is I have 0 to pi over 2. That is sine cubed x minus sine to the 5th x times cosine x dx. Now that's u to the 3rd minus u to the 5th du. Now I don't want to change it into the u's, because if I change it into the u's, then I have to change my limits of integration, or I have to change it back into x before applying my limits of integration. But what I have here is I have 1/4 sine to the 4th x minus 1/6 sine to the 6th x, and I'm going to evaluate it from 0 to pi over 2. Now, if you want to factor in order to make this simpler, I guess you could, but pi over 2 and 0 are pretty easy values to deal with. So let's just go ahead and plug in and evaluate it from 0 to pi over 2. What I have here is I have 1/4 sine pi over 2 to the 4th minus 1/6 sine pi over 2 to the 6th minus, well, this next one's just going to be 0 because it's 1/4 sine of 0 to the 4th minus 1/6 sine of 0 to the 6th, and all of that is 0 because sine of 0 is 0. Well, sine of pi over 2 is, of course, 1. And sine of pi over 2 here, also 1. So really, and of course 1 to the 4th is 1, and 1 to the 6th is 1. So really, what you're getting is 1/4 minus 1/6. That is 3/12 minus 2/12, or 1/12, and that is your answer. Now, alternatively, if I had done it the other way, and I had kept the cosine cubed x and changed two of the sines into 1 minus cosine squared x, and then had the residual sine x dx. Now, the only drawback of this particular one is the fact that this is negative, so I'm going to have to plop a negative out in front. Now, what you could do is use that negative to reverse this difference, which is exactly what I'm going to do. And so as I distribute, I'm going to basically distribute a negative cosine cubed across this so that I get cosine to the 5th x minus cosine cubed x times negative sine x dx. So what I have now is u to the 5th minus u cubed du. 1/6 cosine to the 6th x minus 1/4 cosine to the 4th x, and I'm evaluating from 0 to pi over 2. Well, let's go ahead and plug in. We have 1/6 cosine pi over 2 to the 6th minus 1/4 cosine of pi over 2 to the 4th minus 1/6 cosine of 0 to the 6th minus 1/4 cosine to the 0 to the 4th, and of course it's exactly the opposite of what happened in the last one. Cosine of pi over 2 is 0, so this whole thing is 0 because it's 1/6 0 to the 6th minus 1/4 0 to the 4th. That whole thing is 0. Over here, what I have is I have cosine of 0 is 1, cosine of 0 is 1. So what I have is 1/6 minus 1/4, but the negative of that, which turns out to be exactly what I had up top when I did it according to sine, and it winds up being exactly the same answer. And you know, the fact that the trig makes it easy to go one way and another, this shouldn't surprise us. Now, of course, you know, using secant and tangent, you're not going to run into this. But sine and cosine, since not only are they related, their derivatives are the first degree of the other one, you know, with negatives included and stuff. But that basically is is kind of a neat one because you can do it both ways. That one, there's really no wrong choice. Alrighty, let's go ahead and take a look at this one. Now, if it had been, let's say just for argument's sake, that you had that same interval and you had the same integrand from the last time. I already know, okay? Well, I tell you what, we'll come back to that. But basically what needs to happen here is, no, actually, let's do that. Now, this has symmetry. The question is, what kind of symmetry? Both of these have symmetry, actually. This is an even function. This is an odd function. Odd functions have origin symmetry. And therefore, if I integrate it from negative pi to pi, and it's symmetric about the origin, this is 0. This one, because of its even nature, right, because sine is odd, but sine to the fourth, basically when you raise it to an even power, you're basically unnegativizing the negatives and turning them back positive. This could actually be transformed into just doubling the integral from 0 to pi of that same thing. Now in this case, I don't think it actually benefits you all that much, but you know, just to know that those things are there, especially this one. This one, you don't even have to do the integral to actually know the integral, and so that's kind of neat. Let's go ahead and start working on this one. This one actually winds up being a little bit tough because neither of them are odd. Now we did one earlier that was just sine squared and cosine squared, but this is sine to the fourth and cosine squared. Ultimately, you're going to wind up doing the same thing. You're going to be using some variety of the power reducing, or you're going to be functionally doing the same thing by using double angle identities. So you could set it up as negative pi to pi, and you could do the power reducing for sine, since it's a sine squared squared, and you could do 1 minus cosine of 2x over 2, and you could square that power reducing, and you know, that would be one way to do it. The way that I saw it is I basically pulled sine squared over with the cosine squared. So I had sine squared x, and then sine squared, and let's call it sine x cosine x squared dx. And so I had the makings of the double angle for sine. If I put a 2 here, that's really a 4. Let's put a 1/4 out here. And then this can be transformed into sine of 2x. This can be transformed using the power reducing, which includes a cosine 2x. And it's from there that you can kind of expand out. I don't really care which way you do it. But if you do it this way, just remember that it's probably a good idea to pull out the 1/8, okay? It's also probably a good idea to have this cosine of 2x independent and take the other 1 minus cosine and combine it with the 1 plus cosine, because that's going to give you the difference of 2 squares. And so it'd probably be best to proceed from here. I'm going to go ahead and proceed from this version of it, since that's the one that I saw first. This one, of course, is not illegitimate. You would basically have to expand it out and then sort of just reuse some of the other stuff. Now, this becomes 1/4 integral of negative pi over 2 to pi. Sine squared, remember, is 1 minus cosine 2x over 2. And this becomes sine squared 2x dx. Now, there's obviously a little bit of sort of futzing around that actually needs to happen, but let's go ahead and drop down over here. This is sort of an aside. So this can become 1/8, right, because I'm going to take this half and combine it with the 1/4, negative pi, so that's supposed to be pi, And then basically what we get when we distribute the sine squared across is we get sine squared 2x minus sine squared 2x cosine 2x dx. And of course this right here, if I were to split it into two integrals, which I'm thinking of doing, basically this cosine 2x will combine with the dx along with a 2 in order to be your du. But as I split this apart, what I want to do is I want to basically do power reducing for this sine squared since it doesn't have a cosine 2x with it. And so I'm going to get 1 over 16, negative pi over pi, 1 minus cosine of 4x in this case, right? Because it doubles whatever the existing the angle measurement is. And of course I've taken the over 2 and just pulled it out and combined it with the 1/16. This one right here, I need the negative pi to pi sine 2x, and we're going to put it like that so it actually looks like u squared. And then if I put 2 cosine 2x dx, I need to put a 1/2 out in front, right? But that 1/2 combines also with that 1/8, and I'm going to get 1/16. Whew. All right. Now, we're still cleaning up. I know, these are kind of a bear. So negative pi to pi of dx, okay? And let's actually just leave the 1/16 out in front since it's common to all of them. And I'm going to do minus negative pi to pi of cosine of 4x dx and minus negative pi to pi of this whole thing right here. I'm just going to go ahead and rewrite it just for the sake of being exhaustive, dx, and that is what we have thus far. Now we need to actually go ahead and evaluate it, or actually integrate it, and so we're going to get 1 over 16. We're going to get x minus 1/4 sine of 4x minus 1/3 sine cubed of 2x, and I'm going to evaluate it from negative pi to pi. And when you plug in, this gets a little bit messy, but you have 1/16, okay? Plug in pi, you're going to get pi minus 1/4 sine of 4 pi minus 1/3 sine of 2 pi cubed minus, plug in negative pi minus 1/4 sine of negative 4 pi minus 1/3 sine of negative 2 pi, but that whole thing squared. Well, here's the thing. This is 0. This is 0 because sine of 4 pi is 0. Sine of 2 pi is 0. Sine of negative 4 pi, 0. Sine of 2 pi, 0. And therefore what I really have here is I wind up having 16, or 1/16 pi plus pi, or pi over 8, which is approximately 0.393. And the calculator will confirm that. Now, like I said before, there were several ways to sort of launch into that and to actually perform it. It took me up the whole page, but that's also because I'm writing in pen and I'm writing large so that the document camera can pick up on what I'm doing and you can actually see it. But it is kind of a long problem. It's going to take a lot of identities, basically changing things by means of identity, multiplying it out, realizing what you then have to go through another phase of identities to change, and you just keep using those identities and multiplying, and if it helps you to pull it apart into separate integrals like I did here, then do so. If you don't find that beneficial and you want to actually see it all as a single integral, I'm just emphasizing the fact that these get done term by term, and sometimes it's better to actually put them as separate integrals so that at least in your mind's eye you recognize, oh yeah, what I really need to do is I really need to treat this one with this identity and that one with another identity. And if they're in separate integrals, then they're easier to think of as separate entities that you can employ separate strategies upon. So let's do one more definite integral before we clock out. Now this is, sorry, I need to pull it within the frame so you can see it. This is sine cubed 2x, or sine cubed 2t. Now, what we need to remember is that this means this, right? It's lazy man's notation for that whole thing cubed. Well, if that's cubed, then what happens is you can actually, again, change the form. Let's use the double angle identity and transform sine of 2t into 2 sine t cosine t, and let's cube that. Of course, when you cube all of them separately, you can pull the 2 out in front, and you get negative to pi, and you get sine cubed t cosine cubed t dt. And oh my gosh, we've done one like this before. We know exactly the strategy that we need to use. Let's go ahead and do 0 to pi. Sine cubed t, we're going to change 2 of those cosines into 1 minus sine squared, leaving the cosine t dt to be your du. And basically you need to distribute in order to reveal both terms in terms of u, and you get sine cubed t minus sine to the 5th t, and then cosine t dt. Well, that means that what you have here is you have, oh sorry, that's not supposed to be a 2, that's supposed to be an 8 because it was cubed, right? So 8, I should have just put 2 cubed, but whatever. 8. Now I can go ahead and say, well, that first one is 1/4 sine to the 4th t, and that next one is 1/6 sine to the 6th t, and I'm going to evaluate that from 0 to pi. So I have 8 1/4 sine of pi squared minus 1/6 sine of pi, or sorry, it's supposed to be sine of pi to the 4th. Okay, and this becomes to the 6th minus 1/4 sine of 0 to the 4th minus 1/6 sine of 0 to the 6th. And what I get is, okay, well, that's 0, that's 0, that's 0, that's 0. Oh my gosh, it's 0. Well, that should make sense to us based upon the fact that the period for sine is has shrunk down to 0 to pi. So between 0 and pi, sine of 2t creates one positive hump and one negative hump. That doesn't actually really change all that much when you cube it, and let's go ahead and I'll show you what the graph looks like. If we plug in sine of 2x raised to the 3rd power, and let's go to the window and let's go 0 to pi, and let's basically do it at pi over 4. Pi over 4 will be our scale, and y min is -2 and y max is 2. Well, that makes sense. And so what it looks like is it looks like sine, but it almost looks like it has those weird cubic sort of, it swerves as it goes through instead of going straight through, kind of like when you have a multiplicity of 3 on a polynomial function. As you sort of zero in towards that 0, those zeros look like cubic functions. They swerve as they go through. And you get the same thing here. But notice that from 0 to pi, as you accumulate, this area and this area are going to be negatives of each other, and therefore we get an area of 0. Okay, that does it for the definite integrals. We're going to do a little bit of work with product to sum here in the next video, and then we shall be done. If you have any questions, as always, please do email me. Bye.